Hi students. For the coming mains and MSET exams, I prepared notes from P Black elements. From P Black elements, 15th group elements let us discuss. This 15th group elements are also called as nitrogen family or 5th A group elements will call. So in this 5th A group elements, we have 5 elements. The first one is nitrogen, and second one is phosphorus, arsenic, antimony, bismuth. Here these are the symbols of these elements, and their atomic numbers are 7, 15, 33, 51 and 83. And here I have given electronic configuration of 15th group elements. Nitrogen is helium 2s2 2p3, 3s2 3p3, and here argon is 3d10 4s2 4p3, 4d10 5s2 5p3 is the electronic configuration of stibbium, which is also called as antimony. Bismuth is 14 5d10 6s2 6p3. If you observe all these electronic configurations, the common electronic configuration is ns2 np3, you can say. So common electronic configuration is ns2 np3. That means in the valence shell there are 5 electrons are present. Physical properties let us discuss. First one is atomic size. Atomic size of 15th group elements from top to bottom increases. That's why the order is nitrogen is less than phosphorus, which is less than arsenic, which is less than stibbium, and that is less than bismuth. So this is the atomic radius order of 15th group elements. And coming to the ionization enthalpy, see, ionization enthalpy, atomic size both are inversely proportional. So if you learn atomic size, we can write ionization enthalpy. Just it is reverse to the atomic size. So ionization enthalpy is more for nitrogen than phosphorus, arsenic, antimony and bismuth. Here why ionization enthalpy is more for nitrogen is the smallest element in the 15th group elements. At the same time, removal of electron from nitrogen is very difficult because half-filled electronic configuration, and very important factor is small size. Next, electronegativity. Order of electronegativity top to bottom decreases. So nitrogen has high electronegativity than phosphorus, arsenic, antimony, and bismuth has least electronegativity value. Reason is bismuth is metallic in nature and nitrogen is non-metallic in nature. Next, coming to metallic character. So here metallic character, if you observe, it increases down the group. Down the group, metallic character increases. If you observe the elements, nitrogen, phosphorus, arsenic, antimony, bismuth, the first two elements, that is nitrogen and phosphorus, are non-metals. Arsenic, antimony, these are metallites, whereas bismuth is metal. So down the group metallic nature increases. So bismuth has more metallic nature compared to remaining elements in 15th group elements. And coming to the order of catenation. So catenation is nothing but self linkage of identical atoms is called as catenation. Simply self linkage of identical atoms. So this is called as catenation property. So catenation property is more for phosphorus than nitrogen, than arsenic, antimony, bismuth. So this is the order of catenation property. So that is, you can say it's a decreasing order. Highest is there for phosphorus, least for bismuth. Due to small size and lone pair repulsions, bond energy of Nn is less than expected. So nitrogen shows less catenation than phosphorus. So because of small size, lone pair repulsions, nitrogen shows less catenation property compared to phosphorus. Now nitrogen shows catenation in hydrozoic acid. Formula of hydrozoic acid is N3H. So don't confuse with NH3 and N3H. N3H is hydrozoic acid whereas NH3 is ammonia. So this is the structure of hydrozoic acid, that is HN double bond N double bond N, and there is a negative charge on the terminal nitrogen, positive charge adjacent nitrogen. Next, so oxidation state of nitrogen in hydrozoic acid is minus 1 by 3. So nitrogen can show minus 1 by 3 oxidation state also. This is in hydrozoic acid. And phosphorus shows catenation in its allotropes. So generally we have three allotropes for phosphorus. So they are white or yellow phosphorus, red phosphorus, and the third one is black phosphorus. Let us see one by one properties of that white phosphorus, red phosphorus, and black phosphorus, and their properties, and remaining all will discuss. The first one is white phosphorus, which is also called as yellow phosphorus. Its formula is P4. Even formula for all the allotropes is same. So structure of this white phosphorus, if you observe, so this is the structure of white phosphorus. So in this structure, 3 bond pairs and 1 lone pair is present on every phosphorus. So total number of what you call pair of electrons is 4. So you can consider this as steric number. Steric number is 4, then it shows sp3 hybridization. If hybridization is sp3, it has a tetrahedral shape, geometry. Properties of white phosphorus, if you observe, it is highly poisonous in nature. White phosphorus is highly poisonous and its ignition temperature is very low, right? And when ignition temperature is very low, then it easily catches fire. Therefore it is kept in the water. Simply you can say white phosphorus is stored in the water. Reason is what? Its ignition temperature is low, so easily catches fire. It is insoluble in water but soluble in carbon disulfide. The reason for this is being non-metal. Generally non-metals are not soluble in the water, but they are soluble in non-polar solvents. CS2 is a non-polar solvent, that's why it is soluble in CS2. And when this white phosphorus reacts with sodium hydroxide, then it releases phosphine gas, right? So in this reaction, phosphorus undergoes both oxidation and reduction. So generally you can say disproportionation is taking place. So this is nothing but what? Disproportionation reaction. Same element which undergoes both oxidation and reduction, then it is called as disproportionation reaction. Let us see the reaction. This is white phosphorus. This white phosphorus, when reacts with alkali, that is sodium hydroxide, in the presence of water, then we'll get sodium hypophosphate. Along with that, our desired product, that is phosphine, is formed. So generally phosphine is a poisonous gas. Next, when it is kept in dark, it glows. That's why, so that property is called as phosphorescence. White phosphorus, when kept in dark, it glows, right? That property is called as what? Phosphorescence. In dark, it undergoes slow combustion and emits radiant energy in the form of light rather than in the form of heat, right? Instead of heat, it emits the light, so that is only called as phosphorescence. When heated in the presence of oxygen, it gets oxidized to P2O5, phosphorus pentoxide, which is a monomeric form. Even you can also write it as P4O10. So here white phosphorus, when it is treated with oxygen, will get phosphorus pentoxide. So here I gave the name, that is phosphorus pentoxide. Next, red phosphorus, second allotrope. Structure of red phosphorus is this. So if you observe the white phosphorus, here just now we saw the structure of white phosphorus. So this is the structure of white phosphorus. Here so many phosphorus molecules are arranged as a polymer. So this is is the structure of red phosphorus. It consists of P4 units linked together, due to which it is highly polymerized, and hence it is less reactive than white phosphorus. If you write the reactivity order, so in the reactivity order, white phosphorus is more reactive than red phosphorus, you can say, right? Why white phosphorus is more reactive? Because it is not polymeric structure. Is it clear? But red phosphorus has highly polymerized and it is less reactive. Properties of this red phosphorus, let us see. So red phosphorus is not poisonous in nature, whereas white phosphorus is a poisonous, and its ignition temperature is very high. Thus, it do not catch fire easily, whereas white phosphorus catches fire easily, and it is insoluble in water as well as in carbon disulfide. It do not react with base or alkali, whereas white phosphorus reacted with alkali and gave phosphine gas, and at the same time red phosphorus do not show phosphorescence. When heated in presence of oxygen, it also gets oxidized to P2O5. This property is same in the case of white phosphorus and red phosphorus. The reaction is same. Next, third one is black phosphorus, the last allotrope of phosphorus. Structure of that black phosphorus is this. And here, order of stability of allotropes of phosphorus, if you see, stability is more for black phosphorus, then red phosphorus, then white phosphorus. Stability, reactivity, both are inversely proportional. So stability is more for black phosphorus, so reactivity is less. So simply you can say stability is inversely proportional to reactivity. So reactivity is more for which? White phosphorus. Stability is more for which? Black phosphorus. And this is the stability order of different allotropes of the phosphorus. Now chemical properties, let us see. So here phosphorus is a more reactive element, and it can react with the hydrogens, oxygens, halogens and different types of compounds, and gives different type of the molecules or compounds, you can say. So here let us see, when phosphorus reacts with the hydrogen, it forms hydrides. So generally MH3 type of hydrides are formed when 15th group elements reacts with the hydrogen. So let us see, nitrogen when reacts with the hydrogen will get NH3, which is called as ammonia. Phosphorus will give phosphine. ASH3 is called arsine, SbH3 is called as stibine, and BiH3 is called as bismuthine. So generally the structure of this hydrides, if you see, it resembles pyramidal structure. Hybridization of the central atom, that is 15th group element nitrogen, is sp3 in the hydrides, and shape of the molecule is pyramidal shape. Next, order of thermal stability. So generally thermal stability of hydrides of these 15th group elements down the group decreases, you can say. So NH3 is more stable than PH3, then ASH3, then stibine, then bismuthine. So simply you can say that, so NH3 is thermally more stable. Thermally more stable, whereas BiH3 is thermally least stable. Next, order of reducing character. So here reducing character and thermal stability both are inversely proportional. Here I gave the relation. So here there is a inversely proportional in the relation. That's why the order is reversed. NH3 is the least, then PH3, then ASH3, then SbH3, then BiH3. So here I represented with the arrow also. So here order of reducing character right? Top to bottom, if we observe, it increases. This symbol represents increases. Next, order of basic character. Generally, order of basic character, if you see, top to bottom in a group, it decreases. Okay, so NH3 is more basic compared to PH3, that is phosphine, then arsine, stibine, bismuthine. So down the group, basic character of hydrates decreases with increase in the atomic size. Okay, and here lone pair density at central atom decreases, right? And hence attack of electrophile is nothing but positively charged species, decreases, and it's right. Then basic character decreases. This is the reason why basic character down the group decreases. So here if you see, here nitrogen is there, okay, and here electrophile generally represented with positive side. When it attacks on this nitrogen, attacking of this is very easy because size of nitrogen is very small, okay, and the repulsion forces are less. So rate of formation of NH4 plus is greater than rate of formation of PH4 plus. After nitrogen we have phosphorus, then arsenic, then antimony, then bismuth, right? So here what happens, formation of NH4 plus is easy compared to PH4 plus. Why? Here we discussed already. Next, order of bond angle. Bond angles, if you observe, top to bottom bond angles decreases. Reason is size of the central atom increases. NH3 bond angle is 107.5, phosphine is 93.5, arsine is 91.5, and stibine is 91.3. Almost these are same, 91.5 and 91.3, whereas the bismuthine is 90 degrees. So decrease electronegativity of central atom, bond angle also decreases. As we know that top to bottom electronegativity decreases, bond angle also decreases. So simply you can say electronegativity of central atom is directly proportional to bond angle, right? Or size of the central atom increases, bond angle decreases, you can say, right? So size, if you consider, inversely proportional. Then order of boiling point. Boiling point orders, if you observe, here there is one exception and this is very important. Listen carefully. NH3 bond, that is boiling point, is 238.5. pH3, that is phosphine, is 185.5 degrees. And at the same time arsine is 210, stibine is 254, bismuthine is 290. So generally molecular mass increases, boiling point also increases. So you can say they are directly proportional in the relation. But if you observe, there is no regular gradation in the boiling point. Let's see, ammonia to phosphine boiling point, what happened? Decreased. Again from phosphine to arsine it increased. Okay, so generally boiling point of NH3 is greater than boiling point of phosphine, right? Whereas phosphine is less than arsine, arsine is less than stibine, stibine is less than bismuthine. So there is no regular trend. But anyways, if you observe these two, boiling point of NH3 is greater than pH3. This is due to intermolecular hydrogen bonding, right? Ammonia can form, NH3 can form hydrogen bond. Generally the compound which can form hydrogen bond, its boiling point is more. So that is the reason why NH3 has high boiling point than pH3. Then order of dipole moment. So generally dipole moment is directly proportional to electronegativity, we can say. Polarity we will decide based on the electronegativity, you know. So among the hydrates of 15th group elements, electronegativity is more for nitrogen. So obviously dipole moment is also more for nitrogen than phosphine, that is phosphorus, arsenic, antimony, bismuth. Next, halides. Here this 15th group elements will form two types of halides. One is trihalides, the second one is pentahalides. Let us see trihalides. So generally trihalides are represented with the MX3. So in this, the hybridization of central atom is sp3, Shape of the molecule is pyramidal shape. So there is an exception. Let us see that exception. Except NCl3, NBr3, Ni3, all halides are stable, whereas NCl3, NBr3, Ni3 are unstable. Why these are unstable is low polarity of NX bond, large difference in the size between nitrogen and halogen atom. That is the reason NCl3, NBr3, Ni3 are unstable. Next, Lewis base character in the case of trihalides. In the case of trihalides of nitrogen, let us see. See here, Ni3 is more basic compared to NBr3 than NCl3, NF3. So here, fluorine is more electronegative. It is strongly attracted, and whatever the lone pairs are there, lone pairs are not easily given by the NF3 molecule. But here Ni3 can easily give its lone pair of electron. That's why its basic character is more compared to NF3. Reason, as electronegativity of halide decreases, availability of lone pair over nitrogen atom increases. Hence, Lewis base character increases. Is it clear? So, generally what happens, electronegativity of halides decreases, availability of lone pair over nitrogen increases. So nitrogen can easily give the lone pair of electron. So according to Lewis concept, a substance which can give or which can donate its electron pair is considered as a Lewis base. That's why Ni3 is more basic than NF3. Next, pentahalides. So pentahalides generally represented with the general formula MX5. The best example for this is phosphorus pentachloride. So in this phosphorus pentachloride, if you see the hybridization of phosphorus, hybridization is sp3d. The shape of the molecule is trigonal bipyramidal. Right? So from X-ray study, it is found that solid PCl5 exists in ionic form as PCl4 plus PCl6 minus. This is previous IIT question, which is very, very important. So PCl5, this is existing as an ionic form. Generally P and Cl both are non-metals. Generally non-metals will form covalent compounds. But PCl5 can be exist as an ionic compound in this manner. If you see the structures, PClO4, here there is a positive charge. PCl6, there is a negative charge. Positive, negative both are present. That's why it has ionic character. This is ionic form. So in this PCl4, hybridization of phosphorus is sp3 and shape is tetrahedral. Angle, if you observe, 109 degrees 28 minutes. Why? Here actually there is a lone pair, but that lone pair is donated. That's why it gets a positive charge. That's the reason. Now there is no lone pair. There is no lone pair. So angle becomes 109 degrees 28 minutes. There is no distortions. And coming to this compound, PCl6 minus, hybridization is sp3d2 and square bipyramidal is the shape, or you can also write it as octahedral. Bond angle is 90 degrees. Now solid PBr5 can exist as PBr4 plus Br minus, but not like the PCl5. Sir, see here I gave you note also. Let us see. Nitrogen do not form pentahalides due to non-availability of vacant d orbitals, you can say. So bismuth can form unstable pentahalides due to inert pair effect. Very, very important lines. Nitrogen cannot form pentahalides due to absence of d orbitals, and bismuth forms unstable pentahalides due to inert pair effect. We know what is inert pair effect. It's a reluctance of ns electrons. Next, not only halides, hydrides, even these 15th group elements can form oxides also. So here we have three types of oxides. Let us see what are the three types of oxides. X2O3 type of oxide, X2O4 and X2O5 type of oxides are formed by 15th group elements. So let us see, nitrogen can form three types of oxides, N2O3, O4, O5. Phosphorus also can form three types, P2O3, P2O4, P2O5. Arsenic, antimony, bismuth also can form three types of oxides. So generally non-metal oxides are acidic in nature. Let us see which non-metal, that is what oxide of 15th group element is more acidic and why. So here acidic character, increase in the oxidation number of central atom, acidic character of oxide increases. See here N2O3, N2O4, N2O5. If you see the oxidation states of nitrogen in these three compounds, here N2O5 oxidation state is +5. Here N2O4 is 4, N2O3 is 3. Where more oxidation is there, that is more acidic. Simply you can say oxidation state is directly proportional to acidic strength. Oxidation state of central atom increases, acidic strength also increases. So N2O5 is more acidic than 4 and 3. If oxidation state is same, then with the decreased electronegativity of central atom, acidic character of oxide decreases. Let us see. Nitrogen, phosphorus, arsenic, antimony, bismuth. Down the group metallic character increases, so acidic strength decreases. Nitrogen is more non-metallic, more electronegative, then oxides of nitrogen are more acidic, then acidic strength decreases. So simply left to right in this order I am saying, or you can say group also, right? Or from N2O3 to B2 Bi2O3, acidic strength decreases. Why? Non-metallic character decreases. The oxides of phosphorus, that is P2O3, P2O5, exist as dimers in the form of P4O6 and P4O10. Let us see the first dimer of phosphorus oxide, that is P2O3. Its dimeric form is P4O6. Shape of that molecule is this, right? Or you can also write this structure as phosphorus, 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 phosphorus. Like this also we can represent. Anyway, you can write the structure, and here there is a lone pair on every phosphorus. In P4O6, every phosphorus atom is attached to 3 oxygen atoms. If you consider this phosphorus, it is connected to this oxygen, and this oxygen. Like that, every phosphorus attached to 3 oxygen atoms. In P4O6, total number of pi bonds are 12. Total number of, sorry, not pi bonds, sigma bonds are 12. If you observe here, if you count, you will get 12 sigma bonds, right? 1, 2, 3, 4, 5, 6, 7, 8. This is 8, and 9, 10, 11, 12 sigma bonds are present. And in P4O6 is obtained by heating phosphorus in limited supply of oxygen. Limited supply of oxygen, generally will get this P2O3 or P4O6, limited supply, which is very, very important. So simply you can say that P4 phosphorus, when limited supply of oxygen, then we'll get P2O3. So 4 are there, so 2 moles you have to take, 6 moles, then 3 moles of oxygen, then you will get P2O3. Next, second oxide of phosphorus is P4O10. Shape of P4O10 is this. Simple for this above structure where phosphorus is there, to that you have to write a double bond with oxygen, then you'll get P4O10. In P4O10, every phosphorus atom is attached to 4 oxygen atoms, and in P4O10 is obtained by heating phosphorus in excess of oxygen. That means when phosphorus is treated with the excess oxygen, then we'll get P4O10, right? P4O10, then 2 moles of oxygen you can take, you will get P4O10. So this is about oxides of phosphorus. So this is the part 1 video. In the part 2 video, remaining concepts we'll discuss. Thank you.